Okay, before we calculate the electric potential energy from a system of point charges, let's review some definitions and units and how all these formulas are connected. And this is a little bit confusing, so hang in there. We'll get to the problem in a minute. Okay, recall our units. When we initially were introduced to the electric field, we used the units of force per unit charge, or newtons per coulomb. And then later on, we saw that that is also equivalent to the volts per meter. So electric field can be expressed as newtons per coulomb or volt per meter. Now, electric potential, the symbol V, is just volts. Those are the units of electric potential, volts. And by the way, that is our friend in the lab. That is what we like to measure in the lab with a multimeter, a benchtop or handheld multimeter, the electric potential. That's really a friendly thing to have in the lab. Okay, finally, the electric potential energy, I use the symbol U, big U, sub E, and that can be either expressed as a coulomb volt or a joule. A joule is 1 coulomb volt, so joules of energy. Now, let's go back and look at the formula. Electric field was initially defined as force per unit charge, right? A newton per coulomb. And so we could write force as QE. So either way you want to write that. Now, the electric field later on was defined as the negative change in electric potential over the change in a distance. Okay? Now, I got this special bracket to indicate something that's highly objectionable. We see over here that electric field is really a vector, and somehow we're connecting that to a scalar voltage. So in college physics, we don't really get into the details of how we can get away with this. But nevertheless, so we can write voltage is equal to electric field times distance, right? Now, finally, we have the definition of voltage as the electric potential energy per unit charge. A joule per coulomb is 1 volt is 1 joule per coulomb. But so we can rewrite that if we'd like as electric potential energy is charge times voltage. Now, why did I do this? Because let's look at the formulas for point charges. Once again, the electric force is a vector, and it's that coupling constant K times the product of charges over the distance between these two charges squared. Now, notice what I've done here. Instead of using 1 and 2, I'm using I and J because they can stand for anything. We have to sum things like 1 and 2, 1 and 3, 2 and 3, whatever. I and J are just dummy indices that we can plug in numbers for depending on the number of charges. So I just left it like that in this generic format. So the product of charges over the relative distance between those two charges squared, and then I've got my unit vector indicating the direction between those two charges that you're considering. Okay, so now since the electric field is just right up here, the force per unit charge, we see that it's really the same type of formula, but instead of having a product of charges, we just have one charge in the numerator. Instead of coupling charges for force, we just have one charge. And once again, now we're calculating the electric field at a point in space. So now that distance d sub I for the qith charge is the distance from the point in space to that charge. That's d sub I. I hope you're following me. It's a little bit abstract. Now, once again, I'm going to rewrite the equation for the electric field here again so you can see how it relates to this. So if we multiply this times the distance like we did here, we see that the voltage is just the coupling constant K times Q over distance and not distance squared. See that? See how they're connected there? Voltage is E times distance. So in this case, we no longer have an inverse square law. It's just inversely proportional to distance. And when we're calculating the electric potential at a point in space, we have to know the distance that this qith charge is, how far that is from the point in space we're calculating the potential. Now we'll rewrite that formula, and then we see that since electric potential energy is you just couple a charge into a voltage, you have a voltage in space, and you couple a charge into it, you get energy. So we just multiply the potential by another charge, and we get electric potential energy. And that can also be seen, go back to your first semester. When you have force and you multiply by distance that you're doing work, remember FD cosine theta, I'll leave off the cosine theta. F times D is work, force over displacement. Well, if you multiply this times the distance, this force, you'll see that it's the same formula. But now we have a scalar. We don't have to worry about these pesky vectors out here. Okay, I hope you followed that. It kind of ties it all together the best way that we can for introductory physics. It's a little bit abstract, but some of you, I'm sure, followed that. Okay, now let's look at an example problem, the last one of calculating these forces and electric fields and electric potentials and electric potential energy. This is an interesting case. I do this an interesting way. I call it combinatoric. So let's say we have 3 point charges, and we want to calculate the electric potential energy of this system. This is a system. Now, what's interesting about this, you don't calculate it at some point in space. It just is what it is. But why? Because it only depends on the relative position between these charges. That's all you need to know is how much charge do I have and what's the position between them. Okay, so let's see how this works. Okay, so let's read the problem. Calculate the electric potential energy used to be due to the system, which in this case consists of the 3 point charges shown above. Note, nanocoulomb is 10 to the minus 9 coulomb. Okay, now, by the way, if you see any typos or anything, let me know. Now, for this method, I do this differently than most textbooks. I use combinatorics. I think it's far easier. There might be other people that do this. It's pretty trivial. But anyway, let's look at this. So basically, we're going to have all possible combinations of charges and their associated or their respective distances. So what are the possible combinations of charge couplings? A coupling just being a product of charges. Let's look at Q1. You have Q1 times Q2 and Q1 times Q3. All right? Okay, let's look at Q2. We've got Q2, Q1, but we've already done that. So all we have here is Q2, Q3. So that's it. You've got Q1 times Q2, Q1 times Q3, and Q2 times Q3. That's it. Those are all the possible combinations of charge couplings, where a charge coupling is a product of charges. So see that? So let's go up here and look at this. So we have the total electric potential energy is U12 plus U13 plus U23, where Q1 is, here I give all the parameters, Q1, Q2, and Q1 and Q3 and Q2 and Q3. I believe that takes care of it, and I tagged them with their associated distances. See how the distance between Q1 and Q2 would be 0.65 meter? See that? See that right there? 0.65 meter between these two. And between Q1 and Q3, you got 1.2 meter. Did I put that there? Yes, I did. Q1, Q3, and D13. And then finally, U23 would be Q2 times Q3 times this distance, which is 0.55 meter. There, and that's that row there. There you go. Now you just plug it in, and here's what it looks like. K, Q1, Q2 over D12, plus K times Q1, Q3 over D13, plus K over Q2, Q3 over D23. You can factor out the K, and there's your final formula. And you plug in the values, and that's what it would look like. So there you go. Just look over this very carefully. You might have to stop and think about it. And if you really want to understand what you're doing, you might want to look at these forms up here again to see how it all fits together. It's nice and neat. Physics is very concise and very self-consistent. It is the most fundamental of all the natural sciences. It is the base of all sciences, in fact. And so, it's worth looking into and trying to understand how it all fits together. I hope you enjoyed this brief video about summarizing all the aspects of point charges, in addition to doing an example of calculating the electric potential energy of a system of point charges. Have a nice day.